Hello, everybody. So we're going to talk about Apache Falcon, which we recently incubated, which basically solves data management problems and process management issues that we come in the face in the Hadoop environment. So I am Srikanth. So I work for InMobi as an architect. So I've been involved in the Hadoop community for a while now. And with Yahoo earlier, spent enough time working on data management problems there at Yahoo before I joined InMobi. And I have my colleague Venkatesh. He'll introduce himself.
Hey guys, Venkatesh. I'm an architect at Hortonworks. Work on data integration services and have contributed to different parts of the ecosystem over many years. I, again, have built a couple of data management solutions, 2 generations of data management systems at Yahoo, and we have kind of incorporated the learnings that we have had over these many years, building at scale, and then working with InMobi now to make it an open source software. So let's look at the agenda. We're going to cover what's the motivation behind Falcon, why we had to build something like Falcon, and see what the challenges are in a typical data management platform, and look at overview of Falcon. Let's now see how Falcon addresses these challenges and do a drill down on the architecture and different aspects of how Falcon works, followed by a couple of case studies so that you get a picture of once you understand the architecture, how it's being used in real life. And finally, open for question and answers.
So what actually happens in a typical data processing world is what I put up here. So you have data coming in from various different places, and maybe your machine-generated logs that may reach the Hadoop cluster. You may have databases which may have data which you need to ship into the cluster, which you then use for processing. So ingesting data into the cluster is one of the key problems that one normally runs into in a Hadoop environment. Once you have the data, then you have a lot of challenges in kind of building a processing pipeline over it. So you guys may be familiar with a lot of MapReduce, Pig, Hive, etc., various stuff which allows you to do the processing. But oftentimes these are little application frameworks that will allow you to build components, but when you have to process a large pipeline or which has a sequence of steps that you need to execute, you need to orchestrate them and you need to manage them in its entirety. So that often is a big challenge. Then you may have set up where multiple clusters may be involved, and you may have to ship data from one cluster to another cluster for, let's say, disaster recovery, or even for your as part of your application logic, you may have data to be transferred from one place to another. So that's another common use case and common problem that we normally face. And data that is on the cluster obviously need to be purged. You can't keep infinite amount of data there. So we basically have certain policies around how long can you keep the data, when do you need to throw it. There may be compliance and security requirements there that you need to consider. But when the data is old enough, you need to kind of remove them from the cluster. And before you remove, you probably have to archive them somewhere on a tape-like drive or low-cost storage before they're permanently gone. And once you've processed the data that you have gotten into your cluster, whether it is a clustering algorithm that you're running, or a recommendation system that you're building, or maybe just reporting applications or ad hoc analysis, whatever be it, you may have to ship the data out of the cluster for applications to consume. So it may be just a part of your serving system, or it could be a BI reporting application or a data warehouse that you need to ship them out to. So you need to take this data out of the Hadoop environment for subsequent or for further usage. So here are a number of problems that that we run into. So namely the acquisition part, and then this transformation or managing the pipeline. Then you have things relating to replication or copy, exports, data eviction or archival. All these are problems that we run into while managing data on our Hadoop environment. So what we tried to do was to take these out, these common problems that we are running into every single day, and make them available as a service in the core platform, and free people of the pain to having to manage this on a daily basis, so that the folks who are building applications on Hadoop are focusing only purely on the business logic that they need to implement, or the key functionality that they need to implement, and don't have to bother about all these lifecycle operations that they need to kind of manage. So that is the one of the key reasons why we started to look at this problem and want to build something here. So if you look at the services that we wanted to extract, I'll get a little deep into each of these and explain what they mean. So here are the things that we wanted to extract out as core problems that we want to address. So managing late data that comes into the environment for processing, relay of processes, and then you have data management problems like acquisition, data eviction, or replication. And then you also have to, when you're running large pipelines, you need to look at lineage of data or SLAs of these pipelines. Also consider operability challenges that people may have while looking at the health of the system. So all these are common problems that we need to look at. So let's pick one problem at a time and dwell in it in a little bit of detail, so that we can appreciate what are the problems that we are looking to solve. So one of the important problems that we ran into when going back 2 years when we were trying to build systems for my company, figured out that if you have a lot of processing that you need to do, and let's say a data that arrives on your environment, and you need to process this and produce a derived version of that data, or extract some information out of the data, and that data is further analyzed by, let's say, another set of jobs to extract further value. You have a chain of these processes that needs to happen, and part of the data may need to be shipped outside of the cluster for somebody else to consume. So one of the things that we needed to really do was to make sure that this happens in a continuous relay as opposed to just simple time-based coordination. So if process 1 completes a amount of, does some work that it's supposed to do, the process 2, which is supposed to pick the data from the previous stage, automatically picks it and starts immediately without introducing any buffering or any time lag between them. So we are looking to have a seamless flow of sequence to make sure that we are not losing time while completing this processing and finishing the entire pipeline as per our SLA requirements. So to orchestrate this in a relay fashion was something that we really wanted to get out, and this is something that is required on every single pipeline that we have seen or wanted to build. Right? So that is one thing that we wanted to solve for. The next is we kind of ran into this problem numerous number of times in our environment, where you get a piece of data and you started processing it and you completed processing it. Just after you finished it, you realized that something else at the source has changed and provided new data for the same time period or for the same piece of information that you're looking at. So which means that you'll have to go and redo the work that you did. And we wanted an automated way of kind of handling this late data and do this. And if you have a sequence of jobs, like I was saying in the pipeline earlier, if you have a sequence of this, you have to automatically reinstate the data from each step. So step 1 produced a piece of data, piece of information, and if the source of that changed, then obviously that piece of information would also change if you reprocess them. And that may further be consumed by a subsequent step and so on, and all of them have to be reprocessed if required. So we needed a way to kind of declaratively say how this whole thing has to be orchestrated. So that is another core problem that we wanted to kind of solve as a service and make it available for all the users of the system. So here are these things specifically related to data management. Venkatesh will discuss a little bit about the.
So people come to Hadoop for big data, right? I mean, if you have small data, you don't need Hadoop. But we've seen typically Hadoop clusters, even we had 4,000 node clusters, 6,000 node clusters on outer space. And for capacity planning, we have to purge, the data that's, old enough or become cold and of no use. The second aspect of retention is, compliance, right? You have SOX compliance, and you don't want PIA data to live on your clusters, Hadoop clusters forever, and you have to, create an anonymized version, which is a derived data set, but you have to purge that in 90 days or what have you. And this is a very common recurring pattern that we see, which could be extracted into the platform and provided as a service so that users don't have to write scripts or one-off jobs to actually delete this data in a more efficient way. And it's not about just deletion, right? You could have multiple policies associated with that. Some people want soft delete because there are operator errors, right? If you hard delete, you lose the data. So you want soft delete and have some kind of 14 days or 10 days retention and then hard delete the data or archive the data. And there is also certain race conditions here. If you have your data in your pipeline, if you're replicating the data, which I'm going to talk about next, you don't want to purge the data unless it has been replicated. Or if you have archival scenario, right? You want to archive your data to either tape or archive cluster, Hadoop cluster, which is of course cheaper than NFS and other options. You still want to make sure your data is archived before you return the data. So these are hard problems to solve, which are recurring, and this is a common recurring problem which can take care of that and take care of even the race conditions. The other thing, the challenges that we have seen, at Yahoo and other places that we have worked with, is people use super user privileges for deleting the data because you have user data, and using a super, you have to be a super user to delete the data, and any software bug or operator error could delete your cluster's data, critical data. The other thing is as I spoke about the different criteria for aging purposes, which is a critical thing which we see as a common recurring pattern, which can be extracted out of extracted into the platform. So let's move to replication. So replication is again is a very common concern, right? I mean, you want your critical data, especially production pipelines producing your data or even raw data, to be replicated for disaster recovery purposes, right? But also, we have seen the data itself could be used for processing in other clusters, right? It could be part of your processing pipeline. So we're going to cover in detail, but if you look at local global aggregation as a use case, if you have a large number of clusters or a small number of clusters, you don't want to ship all your data, processed data, over a WAN into your global data center, right? You want to compute local aggregates in your local data center and only ship only those aggregates which are much smaller to your global data center, and then do your global aggregation. So their replication is a critical component of your processing pipeline itself, right? So these are two fundamental things that replication is used, and again, the challenges here is you can't choke the pipe. There are have to throttle the copy because each data center could have different capacity to serve. So you got to make sure you're not choking the pipe, as well as the clusters that you're actually copying the data from. Correctness, right? Data validations, which is missing in most of the ingest software that we see, right? So things like that, and HDFS, again, there are certain version compatibility issues. Of course, with 2.0 we have wire compatibility. With 1.0 you don't have that. So you have to, as a user, if you have to deal with all these different challenges, it's just much easier to have this extracted as service and be provided for users to use. So another one is a common complaint, right? I mean, people have variety of data sources in an enterprise. It's not just a database. So how do you make this, of course there are many tools, and each tool has certain limitations today. So how do you ingest large volumes of data? If let's say you have stuff sitting on a FTP Dropbox or a NAS filer, or even HTTP web service serving data in your enterprise, or even databases, right? So the common challenges here is, again, how efficiently can you get it? Can you do checkpointing? If you have a large terabytes of data that's coming on an hourly basis, you don't want to restart your job if the job fails in somewhere in between. You want to pick up from where you left off, right? You want to do data correctness validations. If your source publishes statistics, you want to validate against those statistics once you've copied the data. you want to format and compress them uniformly, right? I mean, by default, I remember Hadoop compression by default was off, right? So if you don't know about it, none of the data is compressed. So these are some of the common recurring things that we see. And the other thing was, you can't rely on users to adhere to governance policies. So as part of acquisition, if you can create anonymized data set as well as your raw data set with different retention policies, you already have enforced this, and you can have certain class of users have access to that, right? Security is another thing that you can enforce here declaratively so that it's implemented, right? So these are some of the common recurring things, and of course, nobody can deny an operability, right? Every system that you use should be operable, right? So an integrated view of what's happening in your system, based on the holistic information that is, that is collected by Falcon, so that you would know what are the different management functions, the processing logic that's happening at any different point in time. And if you have a complex pipeline, you want to know where it stops, where do I need to restart from, So these are common things which I think allows, if it's extracted into your platform, allows the developer to concentrate on his, business logic, writing his business logic, or deriving insights from the data instead of worrying about these mundane things. And of course, adding alerting and notifications will complete the operability story. So let's move to Falcon overview. Srikanth is going to introduce that.
Thanks. So kind of roll back a couple of years before we started working on this project. So we were actually doing all the stuff that we were talking about here, using custom applications, using standard workflow schedulers. We used Uzi. We could use Scoop and for data transfers, and we used DisCP for replication. We kind of used these bespoke applications, kind of put them all together and started working with it. What we really missed was we actually had a series of steps that we needed to do once the data is generated at the source before it is consumed. So those series of steps hop through many places. So there's a replication that is happening. There is a transfer of a file that's coming from a database back into the cluster. There is a bunch of pig scripts that are running on this data that is reaching us. There are some handwritten map reduce jobs then runs. So there's the sequence of events that are happening, and there's multiple elements of data that are flowing in from various places. So what we observed was that we were able to operate the system with these multitude of small utilities, tools, and applications to orchestrate the whole thing, but we were not able to manage the SLA on a consistent basis of these pipelines. It's simply because we didn't have a good perspective of what is happening in at a high level or at a holistic level. So what we went back and thought, how do we solve for this? So figured out that we need to be able to look at it end to end and not look at it as individual components or individual steps. So one of the first things that we did was we have to create a holistic view of this system, and how do we do that is by generating a bunch of entity definitions. So let me kind of get to what those are. So at the core of the Falcon system is something what we build is called the entity graph. So there are 3 entities that we currently have and support. We'll have more such entity definitions built into Falcon in future. But the 3 of them are cluster, feed or data set, and process. So a cluster is basically a bunch of endpoints that define what a cluster is. And a feed is nothing but a unique location of where a data is on a specific cluster, and it also has information of a lot of meta information, such as what is the frequency of occurrence of this feed, where is it coming from, what is the source of this, where does it need to be replicated if we need to move it elsewhere, how long do we need to maintain this data in the cluster, etc. So the feed basically encapsulates, the feed definition basically encapsulates all information pertaining to a piece of data that has a repeated time-based instances. So that we encapsulated into a concept called field. And then we defined something like a processing logic, which is called as a process. What that does is consume a bunch of feeds and produce a bunch of feeds. So you look at it this way, that there are a bunch of clusters, and feed can be defined on one or more clusters, and you have process which is defined on one or more clusters, but maybe using one or more feeds and may produce one or more feeds. So that in a way allowed us to look at this entire thing fairly holistically, because now I know that there is a data that is coming in, let's say in feed 1, and that is used by process 1 and it is producing feed 2, which I have already defined, and the third process maybe or second process may use feed 2 and may produce something else. Now the definition of a element of data is defined, is there in the system only once. A feed is defined only once, and all producers and consumers reuse that definition and kind of inherit the properties of the definition. Similarly, a process is all the core logic of a single process, which may in turn be a workflow, is also defined inside one single process definition. Merely by putting these higher level abstractions of this data elements, the processing elements and the execution elements in these entity definitions, and creating this dependency graph inside the system allowed us to understand the entire flow of where the data is flowing, how is it flowing, where is it stuck, everything is fairly visible. And the operability that Venkatesh was talking about earlier can be built easily by understanding. Let's say if we didn't get the data, then we will know at what point in the pipeline is it stalled, because by walking back on the graph from a feed, you would get back to the original source of this data all the way to the root, and you would know where exactly is it stuck. So you'd be able to figure that out. So the dependency graph is in a way core to what Falcon, it defines Falcon in many ways. So that is what we started with. So that would allow us to create a fairly abstract view of what data is present, how is it processed, where is it processed, and how often it needs to run, how frequently it needs to run. All that is all encapsulated within these three entity definitions. So that is really the core of this system. Coming to the architecture, so Falcon doesn't do any heavy lifting other than kind of allowing for this metadata to be stored within this system. So it basically has its entity definitions, it keeps them in its state, but all the scheduling functions or execution, it basically delegates it to the workflow engine, and what it does is it instruments users' processes with some Falcon steps. It embeds them in it so that it can listen in to every single action that the user function is doing. Say for example, if I have a pick script and I need to execute that, what it does is it creates a Uzi workflow, puts the pick script in it, and also puts some steps for post-processing, allowing us to, Venkatesh will walk us through those details a little more in a bit, but the architecture is fairly simple. So it doesn't do anything heavyweight, it delegates all the responsibility to the underlying system, but it just gives a complete global perspective of what is happening. So you'd see that there is simple REST APIs available for you to define and configure the entities or modify the entities, allows you to look at the state of each of the entity in the system, and also look at the instance states of the execution state of each of the instances. So for example, if I have a hourly process and it needs to run every hour, then I can actually go and look at this and say, tell me what happened last hour, all the process that happened last hour, and how much of it was successful, etc. I can actually look at a feed and say, given that this feed is what I'm interested, tell me all its roots, or from where this feed is inherited from, or this data is inherited from, and tell me if in each stage have they been successful in completing their work. You will be able to kind of track that down to where exactly is it stuck, or is it healthy, is it progressing well, all that you will be able to figure out. So apart from that, H catalog integration is still not there, but it's coming. So the idea is to provide a one-to-one correspondence between a feed definition that we have in Falcon with a H catalog definition, so that they are all there is no duplication. So what is present in H catalog will not be duplicated within Falcon, but just coexist and operate well. So that's the architecture, and Venkatesh will cover a little bit of how things are scheduled.
So I wanted to add to this one. Basically, all the user entities that is input into Falcon by the user is stored on HDFS. So there is no state, there is no database maintained. The entity graph that he spoke about is, is an in-memory structure that is maintained within Falcon, and if it dies, you can bring up another server and it reads off of the config store. You can choose which HDFS it'll store this configurations and build that entity graph into memory. So in terms of just drilling down under the hood, so the feed essentially encapsulates metadata about what all clusters is this feed present in, and for each cluster you basically say what's the retention policy, right? If you have multiple clusters that this feed is present in, you can if you have tag one cluster as source, another cluster as target, automatically the data is replicated. So these are inferred by Falcon based on the DSL that is input. And he spoke about late data handling, right? So there are primitives, declarative primitives in Falcon where you say, what's the late cutoff? I mean, how long can I get out of band data? So if it's, let's say, an hourly feed, for that particular hour, maybe I have 60 minutes, 60 more minutes, or 120 more minutes is the cutoff. So I can listen to until that interval for that instance and re-trigger the processing. So all this is captured by Falcon, and it knows holistically what are the things I need to instrument now for it to be orchestrated and executed, right? So from a feed, of course, I need to know what clusters, right? First, you need to define cluster, which is the infrastructure endpoint, right? I want to call it infrastructure because we have many more data sources apart from a cluster. So once you know what the infrastructure is, the feed participates in multiple clusters. So based on inferring data from these two entities, it creates multiple scheduled recurring workflows. So one is we spoke about retention, right? You want to evict this data as soon as the data is expired. So you create a schedule for that, which is a coarse-grained one. It really does not map to the frequency of the feed because you want to have a coarse-grained retention. So that is one schedule, and there's a workflow which basically goes and sees what are the candidates or what are the instances or what are the partitions that are candidate for purging, and it purges them from HDFS or based on the policy that you have configured. The second workflow is for replication. If you have configured multiple clusters as one as source and multiple of them as target, then there are multiple replication jobs that needs to be orchestrated. So the other thing it does is now it creates a scheduler functionality in Uzi, which is the coordinator, saying, okay, if this is an hourly feed, as soon as the data becomes available, if it's raw or processed, what have you, it now takes and creates a replication schedule and creates a workflow corresponding to that schedule to say copy this data as soon as it becomes available from the cluster the source cluster that you have configured. So you don't have to deal with Uzi, you don't have to deal with the CLI part, you don't have to know Uzi XML, but declaratively when you do this, automatically behind the scenes, all this is generated, auto-generated, and registered with Uzi and being monitored when the executions happen, right? So that's the first part, which is the workflow generation, and then the registration with Uzi. So other value-added pieces that you get is there is some kind of pre-processing and post-processing that are slapped onto the user's process, which is here retention and replication, right? So to give an analogy, it's very similar to AspectJ, right? You're essentially taking out cross-cutting concerns outside of your main code and having it added at runtime, right? So essentially that's what Falcon does. So you write your business or you express your business logic, and it does some pre-processing and post-processing and adds that into your workflows. So the cool thing it does is for late data handling, as I was saying. So it records the data set when the process was triggered, right, or when the replication was triggered. If the data changes, the replication has to be rerun, right? So it records that as a pre-process, executes whatever it needs to execute here. In the case of replication, it replicates the data, and for post-processing, it does two things, right? There is a JMS notification as part of the post-processing for even users. Users could subscribe to topics and get notifications per instance, per group, what have you. And Falcon also listens to notifications for doing retries, late data handling, things like that. So, and also for operability concerns, we copy, the task tracker logs, the Uzi logs, all the logs, and make it available for users through CLI to look at these logs for debugging purposes. And of course, you don't have to do anything when we have edge catalog integration. Once this happens, once there is a replication or ingest, automatically, that partition will be registered in edge catalog as a partition. And when there is a purge or eviction, we automatically deregister that partition or drop the partition from edge catalog, which is free, so that you could write Hive queries or listen to notifications, do something else outside of Falcon. So a process schedule is very, very similar, except that this is again there is no data management functions here, but we have the same very similar value-added services, which are pre-processing, how to handle this late data. If you have a series of feeds as input to your process, if there is late data, what is your late processing policy, which you have specified? So that is executed. Again, the post-processing very, very similar to what is done in feed. So if your process fails for some reason, right? So Falcon knows, and there is a coarse-grained retries. In Uzi, the retries are transient, right? You could of course configure, but you have to change the Uzi site.xml. So here you have a coarse-grained retries, and you can configure what policy you want for retries. Is it you back off, or it's periodic, or exponential back off, and things like that. So physical architecture. So one thing different with Falcon is it works there is an instance of Falcon in a colo, unlike other components in the ecosystem. So most of it is one per cluster. If you have multiple clusters within a colo, you run edge catalog, Uzi, every other component is one per cluster. So Falcon, we decided to have one per colo because you don't want one working across, because data centers may be down or the network may be down between data centers. And we also have a component as part of Falcon called Prism, where you could input your DSLs, and it's a very thin veneer, which essentially farms these requests to the individual Falcon servers running in each colo. So I'm going to cover a simpler case study and leave the InMobi complex case study to Srikanth. So you have multiple clusters, right? So let's look at there are different processing you could do to your data. So you have stage data. You first get your raw data and stage it somewhere. And just because you want this raw data, if things go down, if your data center goes down, or for whatever reason you want to continue this processing in another data center, so you can configure in a feed which is the stage data to have a second cluster as the target, so automatically you get replication for free, right, to a failover Hadoop cluster or a BCP cluster, right? Then you go through some processing. Let's say you cleanse your data, then you confirm some kind of conformed data, some more massaging. And once you've done generated aggregates or whatever which is presentable to tools, that is a feed again within Falcon, right? So that feed also has another cluster. You choose to replicate that again, right? Because your BI tools, if once your processing is done, if that goes down, your BI tools or reporting tools would not be able to access the data. So you may want to BCP that data as well. And your tools can, BI tools can read the data off of JDBC, ODBC, what have you. So Falcon essentially, manages. You declaratively specify to Falcon that these are my feeds, these are my processing, which is you write your pick scripts, Hive scripts, whatever you're used to doing. But all the orchestration, scheduling, managing, reprocessing if things go down in the middle, all that is essentially handled by Falcon. So let's look at retention here. So this is cool, right? I mean, you have different feeds and maybe on different clusters. Each cluster, you can specify retention for a given feed, right? You may BCP this, but your raw data you want only for let's say 3 months, right? Or even a month, 30 days. But you want the BCP cluster to have it for 13 days. Maybe that's your historical warehouse where you archive all your data and do ad hoc analysis. You want it for 13 months. So you can specify these different retention policies, again, very simple declaratively with different policies for each cluster. And Falcon orchestrates that and essentially executes it. So in summary, you're basically simplifying your data management needs using Falcon for audit and compliance purposes. So I'll let Srikanth talk about distributed processing.
Thanks. So this is one of the pipelines, if you will, that we run at InMobi that I wanted to kind of talk about. Yeah. So little bit about what InMobi is. InMobi is basically one of the leading mobile advertising company there. So we have about 6 clusters in our setup. We have 4 data centers geographically distributed, and we have 1 cluster in each of them, and then we have 2 clusters in one of the global colos or central colos. Have a petabyte of storage across these clusters, and we get 5 terabytes of new data every day, and about 20 terabytes of data is processed in these clusters every single day, which is like 5 terabytes of today, and some historical data are used for analysis and stuff like that. So our clusters is about 200 nodes, and we run about 175,000 jobs, Hadoop jobs a day, and 60,000 Woozy workflows in a day. So in Falcon, we kind of have about 300 feed definitions and 100 process definitions, and some of these feed definitions and process definitions span across multiple clusters. So that's roughly the stats about what our clusters and what our environment is. So more specifically about the use case that I'm going to talk about is that we have ad request data that comes from the end users, which we serve on which we serve ads, and then impression render event comes back to us from the user saying that the impression is rendered on the device, and then the user may or may not click the ad and then click data, and then followed by a conversion event, which could be some goal that the advertiser has set. So each of these data is coming to us in independent streams, and they are streamed minutely using a system called Conduit, which we have built and open sourced also, which largely is based on Scribe, which was open sourced by Facebook. We kind of took that, modified, and using it for our purpose. So we get minutely logs from these streaming events that we get into our cluster. So then we try and take each of these event streams, that is impression, click, and conversion event, which are fairly small in size, and join it with the ad request event to kind of extract more information that are available at request time. And this information then goes through, after the join process, through a summary generation, and this happens in one data center. And the summary is generated every half hour based on the minutely logs that we get, and the summary basically consumes feeds that are coming from a database for metadata and information that our customers put in. So these summaries are generated every half hour. And then what we then do is take data that is generated by each of these data centers and ship the data from each of these small data centers every half hour back to a global data center, and that is then aggregated further to create a Uber data set that is used by some of our feedback systems and reporting systems, etc. So that is largely the complete example that I'm going to talk about. So in this particular case, you would find that there are a number of data elements, and this processing is defined in multiple data centers, is happening in multiple data centers, and then data is replicated and then finally summarized. But in Falcon, if we were to define this, what we would do is just have 4 definitions for 4 feeds, which is request data, impression data, click data, and conversion data, define the frequency and all the properties of this feed, and just state that this data is now available in each of these 4 data centers. And then we have a bunch of feed definitions corresponding to the metadata that is coming from the database, and 1 feed definition for each database data element. And then we have only 1 definition for the hourly summaries. Now, with just these 5 feed definitions and 2 process definition, one is the enrichment process and second is the summary process, the entire orchestration happens. We don't have any other configuration, any other information. With just these 5 feed definitions and 2 process definition, we would be able to get to know the health of this entire processing pipeline on a every half hour basis or 1 hour basis, and be able to track SLA misses, track where things are stuck automatically. If we were to do it through custom individual tools and built this whole thing, we had it that way for a while, and it was fairly complex and difficult to manage. It was fairly nightmarish to handle that. So with Falcon, it's fairly a breeze right now to manage this whole thing. So I think we're almost out of time, but yeah, that's broadly what I wanted to cover in the case study.
Just to summarize what's coming in the future, we are working on security. Currently, it works with insecure, non-secure Hadoop clusters. We want to make sure it works with secure Hadoop clusters. Again, Falcon, you could embed, the user processing is expressed as a OZ workflow today, but I already have a patch available in the open for embedding pick scripts, and we want to, as soon as we have edge catalog integration, you could embed, MapReduce jobs or even Hive scripts as your processing element instead of a complex OZ workflow. Data acquisition, we want to do file-based. I think we have learned our lesson that getting data, large amounts of data from a database is just hard, and writing connectors for different flavors of databases is again a non-scalable solution. So instead, leave it to database DBAs to dump the data using their favorite tools on a filer and SAP the data. Where we could provide checkpointing, do validation, check some validations, and much nicer things with files. Again, monitoring management. Currently, everything is CLI. There is a REST API for Falcon, and CLI is a wrapper or REST API. So we would have, at least to start with, we'll have a monitoring management dashboard and eventually have a UI for inputting the DSLs as well. Just to cover highlights again, Falcon covers both data management and data processing functionality. So there are some available as we spoke. Most of the things we covered has already been there in Falcon, but there are some coming as well. So in the interest of time, we are open for questions, and we request people, if you have questions, come down to the mic and we can. And by the way, the website is up, and I encourage people, whoever is interested, to subscribe to the mailing list. And of course, contributions are welcome. Oh, no question. Okay.